Welcome to this video. In this video, we will see the representation of floating point number. That means how the floating point numbers can be represented. So these are the outlines of the video. First, we will see the floating point number representation, then the IEEE floating point number representation, and then we will take one example to see the floating point representation of a number. So now let's start with the floating point number representation. So for in the floating point number, there are mainly two parts. The first part represents the signed fixed point number, which is called the mantissa, and the second part is designated the position of the decimal or binary point called exponent. The fixed point mantissa may be a fraction or an integer. The floating point is always interpreted as to represent a number in the following form. What is the form? This is m into r to the power e, where m is the mantissa, and r is the radix and e is the exponent part. Okay. So in the diagram, we can understand these things very clearly. So as you can see that this is the first part and this is the second part. These are the two main parts of a floating point representation. Along with this part, one bit is kept to see whether the number is positive or negative. That means this is the sign bit. This bit represents the whether the number is positive or negative. So this first part is called the exponent part, and this part is the mantissa part, or also called the significant f part. Okay. So if we represent a number with the help of this notion, that for decimal numbers the representation will be something like that. That means this plus minus indicates whether the number is positive or negative, and this 1 point y, that means this is stands for the mantissa, 1 point mantissa, into, for decimal it is 10 to the power, that is the radix, 10 to the power x, that means the exponent part. Similarly, if it is a binary number, then similar, the plus minus which represents the positive or negative number, then this y represents the your mantissa part, and this x represents the exponent part, and this is 2 is the radix for the binary numbers. Okay, I think it is understandable. So now some other important thing of floating point representation. Now we'll see. First, that the floating point number is said to be normalized if the most significant bit or the most significant digit of the mantissa is 1. So in the last slide, we'll see the two portion of a floating point number. First is the mantissa and the exponent. If the most significant bit of the mantissa is 1, that means the floating point number is normalized. Second thing is that the signed integer and exponents are represented either signed representation or 1's complement representation or 2's complement representation. That means the signed integer or the exponent part, that means the mantissa and the exponent parts can be represented either in signed representation or 1's complement or 2's complement representation. So now let's see what is the condition for sign bit. If the sign bit, which is the first bit of the whole number, is 0, if it is 0, then it is positive number. If it is 1, then it is negative number. That means the positive and negative number is signified by the first bit, and if it is 0, then it is positive number. If it is 1, then it is negative number. Okay. So now one most important thing is that the non-terminating binary numbers, that means the number which are not terminating in nature, that is the non-terminating binary numbers cannot be represented in floating point representation. So let's take an example, 1 by 3. 1 by 3 can be represented in this way, but it is a non-terminating. Okay, that means after the point there are some continuously repeating bits are there. So this type of numbers cannot be represented by floating point, simple floating point numbers. Okay. So now let's see the IEEE floating point number representation. So the IEEE, as you know, that gives some standard for the representing the floating point numbers. So this is the representation of the numbers in IEEE format. The first is the sign bit, next is the exponent, and next is the mantissa. So these are the basic three parts which we have already discussed have in the IEEE format, and the representation of the number is something like that. This -1 to the power s. S is represents the this whole thing, -1 to the power s is representing whether it is a positive number or negative number. Okay. So if s is equal to 0, that means -1 to the power 0 is nothing but 0. That means it is 0. That means it is a positive number. If s is equal to 1, that means ultimately result is -1. That means the whole number is negative. The next part is the 1 plus m. M is the mantissa part. And what is that 1? 1 is the most significant bit of the result. And we know that this most significant bit should be 1. So that's why this is written here as 1. 1 plus m into 2 to the power e. So for binary numbers it is 2 and e is the exponent part. Okay. So according to the IEEE 754 standard, the floating point number representation can be done in the following ways. So first we have in IEEE designates the numbers depending on the total number of bits. So first representation is the half precision representation. In half precision representation is represented with the help of 16 bits. So in this 16 bit, 1 bit is reserved for the sign bit, 5 bit is for the exponent, and the 10 bit is for the mantissa. So next representation is the single precision representation. In single precision representation consists of total 32 bits. In these 32 bits, 1 bit is for the sign bit, 8 bit is for the exponent, and 23 bits are for the mantissa. Next representation is the double precision. In the double precision representation, total 64 bits are used. Out of this 64 bit, 1 bit is for the sign, 11 bits are for the exponents, and 52 bits are for the mantissa. And the next representation is the with the help of the 128 bits. So out of this 128 bits, 1 bit is for the sign bit, 15 bit is for exponent, and 112 bits are for mantissa. So these are the standard IEEE standard representation of the floating point numbers which are used in practice or practically which are used. So now some special values are there in IEEE representation. So let's see what are that. First, that all the exponent bits, if all the exponent bits are 0, with all mantissa bits 0, this represents the number is 0. That means if all the exponent bits are 0 and all the mantissas are also 0, that means the total whole number is 0. So now depending on the sign bit, the number will be either +0 or -0. Okay. Next is that if all the exponent bits are 1 and the mantissa bits are 0, which represents the number infinity. Now if the sign bit is 0, then it is +infinity, and if sign bit is 1, then it is minus infinity. Next is that if all the exponent bits are 0 and the mantissa bits are non-zero. In this case, it represents the denormalized number. Okay, and the last representation is that if all the exponent bits are 1 and mantissa bits are non-zero, which represents an error. That means no result will come. So these are the IEEE floating point number representation. So now we'll check one example for floating point representation of number. So for that we'll take the 32-bit representation format. So in this 32-bit, as we know that 1 bit is for signed, 8 bit is for the signed exponent, and 23 bits are the fractional part. So the leading bit, that is 1. What is the leading bit? That is the most significant bit. The most significant bit is always 1 and it is not stored. Why it is not stored? Because if the number is normalized, then it will be always 1. So, and it is not stored, and it is also referred as a hidden bit. Okay. So now if I take one example of minus 53.5, and if it is normalized, then the binary representation will be something like that. And if this is the binary representation of the minus 53.5, and this is the generalized form for floating point number. Okay, and this is actually how we'll represent. In this way we can represent. That means this number, that is this number, which is the generalized form of the floating point number, if we represent with the help of the representation with the help of IEEE, then the mantissa are stored here and the exponents are stored here, and this is the sign bit. So here you can see that this is minus 53, that's why the sign bit is 1. And here you can see that this exponent is 5. So now this is 101. So this 101, that means it is 5. And the rest part, this is 101011. This 101011, this is the, this part is represented in the higher bit position of the mantissa. And this we can see that this 1 is not stored. So this 1 is the hidden bit. Okay. So in this way we can represent one number in a floating point representation. Okay. So where this number is the 8-bit representation of the exponent, that is it is 5 plus 5, and the 8-bit exponent field is used to store the integer exponents of minus 126 to plus 127. Okay, so in this way, with this example also, we can understand how the floating point numbers are represented. Thank you for watching the video.